Hello, Kasakya Denis Nicholas, alongside my comrade Musasizi Jr. will be taking you through machine learning. Uh, Machine learning is a field of study that gives computers ability to learn without being explicitly programmed. What does this mean? It means the models are just given features in form of maybe images to learn from instead of being given rules or step-by-step instructions on how to execute the tasks. So a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Here it means we have during the making of the models, a model is specifically a representation of a certain phenomenon. Uh, there is what we call utility, what's the expected utility of a model, how it's supposed to perform. So there's something called the performance measure, which is it is assessed whether it meets its utility. So we have two types of machine learning, that's supervised and then unsupervised. Unsupervised, it requires labeled dataset, and for unsupervised, it uses unlabeled dataset. Dataset is just data ready to be fed into the model, and training is the process. So you shall have to contrast traditional programming and then the machine learning approach. In the traditional programming, we had to write the rules or the code to execute the models. But for the case of machine learning approach, here you just have to train the model with data sets. An example I can give is uh, an image identification model. Maybe for people or for animals, you can feed it with various images from which it can use to make further predictions in case maybe you have presented an image of a person or an image of an animal. It can be able to do the prediction based on what it has been learning. We have supervised machine learning in detail. Under this, we have regression and classification. And regression, it is basically dealing with continuous data types that are numeric in nature. Then for classification, it deals with discrete data types. And for regression, the examples you can have the prices of maybe houses or household items. Then for the case of classification, we can have categorical variables, which can be the cases of a car or dog, for instance. Then unsupervised learning, because the features represent information. This can be the case of images, and as the model studies the features, it gets more information, and it learns from the features using algorithms such as clustering and anomaly detection. Under clustering, we group items sharing common characteristics. You can say students having a common course, sharing a common meal, something of a sort. And then anomaly detection, it detects unusual occurrences in instances. For example, in a credit card fraud detection, variations in the spending can cause an alarm in the case, and it could be a detection for fraud. Then we have k nearest neighbors, which is abbreviated as KNN. It's a simple versatile supervised machine learning algorithm for classification and regression tasks. So under here we have parametric and non-parametric models. For parametric, you know which model exactly will fit to the data. And then for parametric models, the data tells you what the model will look like. To implement KNN, we shall have to calculate the distances between the training data and the test point. Test point can be a point that has an object that has been introduced within a surrounding. For example, it can introduce a point in between circles and triangles. So we shall have to calculate the distances, then find the nearest k neighbors by sorting pairwise distances. We use Euclidean and Manhattan distances. This I'll discuss in the next slide. Then we shall classify the point based on the majority vote, which ones maybe are many, whether the circles or the triangles. So the majority take the test point. We have use cases for KNN. Here we have text mining, agriculture, and then cargo competition. Earlier on, as I told you, uh, Manhattan distance and Euclidean distance. So for Euclidean distance, the dimensions measure similar properties. You can take the case of width, height, and then depth. For the case of Manhattan, there are different dimensions that are measured. For example, age, weight, and gender, there is no correlation at all. Then the advantages and disadvantages of KNN, it's
Man, what happened? Huh? Nicholas.
as I was, you have the pros, pros and cons, and as earlier I told you, we have it can be easily used with multi-class datasets, and it can be used for both regression and classification problems. It requires no assumptions in data distribution, and it's easy to explain, simple to understand, and extremely powerful. Then the efficiency of the algorithm declines very fast as the dataset grows. That's one of the disadvantages. Then the cost of making prediction steps is relatively high, and it suffers from skewed class distribution, and it doesn't work where there are missing values. And at the end of that, I had the certificate is there. So I hope my colleagues can take you in the next modules.
Right. Thank you, Nicholas, for the explanation of the first part of the course. I think you can now stop sharing and I share my screen for the second part of the course. Um, I shall begin with, okay, I shall explain the three parts in the second part of the course, which shall be ensemble learning, support vector machines, and then principal component analysis. I shall begin with ensemble learning. Again, my name is Junior. Ensemble learning is where prediction of models is where we have prediction of models, or which you can call weaker models to make stronger ones, which are more reliable and reduce errors and improve performance. Ensemble learning is in two types, or has two types, where one is bugging and another one is boosting. Bugging is where we have our models trained on independent datasets, and we average the results. Then boosting is where we train our models sequentially on similar data, and each of the models will be learning from the mistakes of the previous one. Each of the types of ensemble learning have a series of steps or algorithms that can be followed, where bugging has bootstrap sampling, base model training, prediction aggregation, then final prediction. I also listed here the algorithms of boosting, where we first initialize the model weights, then we train weak models, and then we do sequential learning. And then after that, we have also random forests, still under ensemble learning, which is a collection of decision trees that work together to make predictions. It takes different random parts of the data set, train each tree, and then combines the results. This approach, of course, improves accuracy of the prediction. It has features like handling missing data, scaling with large complex data without skill and performance degradation. Still, when we are working with random forests, the algorithm is versatile and it can be applied to both classification tasks and regression tasks. When we are dealing with random forests, we have some assumptions like each tree making its own decisions. We need enough data. Of course, when you are dealing with random forests, shall need to have enough data. And then random parts of the data are used. And when we use different predictions, random forest shall be improving the accuracy. So random forests have disadvantages and advantages, where I listed some of the advantages, like working well with nonlinear data. Then also lowers the risk of overfitting. Also runs efficient on large data sets. Then it's good when you have some instance of outliers. Then the disadvantages can include slow training, as I listed them here. Sometimes it's not suitable for methods. Okay, not sometimes, but random forests are not suitable for linear methods with a lot of sparse data features. Then storage based when we're dealing with categorical variables. Then after that, greedy algorithms don't use robo-optimum tree structure. Still under ensemble learning, we have what we call auto boost, which is a technique of combining multiple weak classifiers to come up with one stronger one. And these classifiers progressively learn from other longly classified objects. We have strong classifiers and weak classifiers. The weak classifier is the one that performs better than random guessing. Then we have, after that, I can talk about support vector machines. I shall summarize because of a time constraint. So a support vector machine, it's a machine learning algorithm that's used for both classification and regression tasks. Under support vector machines, we have what we call margins and correct classifications and maximizing classifications. So support vector machines, the reasonable choice for the best hyperframe is one that maximizes the separation margin. I shall talk about the margins in the coming slide. And then on top of correct classification, so we have the best hyperframe already separating the given classes better. The hyperframe is like a line of best fit, or when it's of more dimension, it's when we call it a hyperframe. Then with maximizing classification, the distance between the nearest data point and the hyperframe is most cared about. Then if there are outliers, SVM is good at detecting them and ignoring them. And then nonlinear hyperframe. I'll introduce some two squares using the Kano slides. So let's say they shall talk about margins, two types of margins. A margin is the distance between the perfect spreads the data point between different classes without any misclassifications. And then a soft margin is the opposite of the hard margin. We have the kernel trick. As I told you, I should talk about the kernel. This computes the dot product of the feature vectors, which is sufficient to classify linearly separable data. It has types like polynomial, Gaussian radio basis function, signal kernel, and then cosine similarity kernel. Then we have after that using support vector machines with linear data sets and non-linear data sets. Linear data set is the one-year data set, the opposite of this. So the data can't be perfectly separated by a straight line. It has advantages using linear kernel on a linear data has some advantages like efficiency, simplicity, and scalability. And then with non-linear data, have some kernels like polynomial kernel, radius-based function, radio-based function, the sigmoid kernel, and then SVM can also be applied to regression, where it maximizes the margin between the classes and the only points outside the epsilon margin contribute to the term the regression line. And it's called support vector. We can use a sphere for a female voice according to the features. When you create a machine learning model that will help us to follow a series of steps, whereby first, which we shall do data preparation for your data set containing the samples, male and female voices, which are post-labeled for the machine learning model to learn. Then feature extraction, where audio files will be converted to numerical features, and then have data processing, where we normalize features to ensure values are in the same range. Then unsupervised machine learning trained the first part, which was supervised. First which is used of number of clusters. This is which is the where so is possible in the data set. It can be applied in data visualization, noise reduction, feature selection, and more. It has swimming linearity and more as I listed them here. Thank you. That's it for now.